Okay, so you might remember convolutions from your differential equations class. Convolutions in the context of Laplace transforms, especially like the way that it usually gets taught in a differential equations class, they seem like it's a different definition than the definition we're about to give here, but it's actually the same definition, and we can talk about why it's the same definition if you want in the discussion forums. But the definition is the following. Whoops. The convolution of two functions. Okay, and look in the book for more discussion about what convolution is, but this is going to be equal to the integral from minus infinity to positive infinity f of x minus y g of y dy. But one way to think about this is we are taking a weighted average of f with respect to the weight g. That's one way to think about it. We're sort of centering things at x and taking a weighted average of f with respect to the weight g. And now we want to compute the Fourier transform of the convolution. So when I say that, what's happening is you're given two functions, f and g, and you get something that's smooth. It sort of smooths things out. And actually, if we come back to our example here, talking about weighted averages, notice that we can view something like this as a convolution of psi with the function sine kx over pi x. And now we're letting the limit as k goes to infinity, and we're looking at weighted averages of psi centered at x anyways. Okay, so that's one way to think about it. Okay, so what's happening here, if I want to take the Fourier transform, I'm just going to look at the definition of what the Fourier transform is. That's kind of a good piece of advice for a lot of these problems. I want to compute the Fourier transform. Okay, on the outside it's going to be minus infinity to positive infinity, the convolution of these two functions, and then e to the minus I cx dx. Okay, so now I want to replace my convolution with the definition. Okay, so I just need to be careful here. This is going to be equal to the integral f x minus y, careful meaning I need to get everything in the right order, g of y, dy, e to the minus I cx dx. But I just want to write this like, I want to put the dy on the outside or on the inside like this. So I don't want it here. I want to write it like this. E to the minus I cx dy dx. And now basically, because I know what I want to do here, I'm going to multiply and divide by 1. Or multiply by 1. So what I mean by that is I'm going to have f of x minus y, g of y, e to the I cy, e to the minus I cy, or sorry, cx, e to the minus I cy, dy dx. Okay, now since both of these functions, f and g, I didn't say it, but both of these functions are integrable, what I want to do next is swap the order of integration. So I'm going to have minus infinity to positive infinity. Okay, so the dx integral is going to be the integral on the inside. And so on the outside, I'm going to have g of y, e to the minus I cy, then times the integral minus infinity to positive infinity, f of x minus y, e, and now I'm going to combine these into one exponent, minus I c x minus y dx, and then dy. Okay, and I don't want to completely rewrite this whole inner integral, so I'm going to make a change of variables. In other words, do u substitution. I'm going to say u is equal to x minus y. So then du is equal to dx. And this integral is going to become the following. Notice normally I need to change the limits on the integral as well. But if u is equal to x minus y and x is equal to infinity, then infinity minus y is still infinity. So the limits are going to stay the same. That's very important. I'm going to have u here and a u here. Okay, and so now what's going to happen? I'm going to have my integral on the outside, minus infinity to positive infinity, g of y e to the minus I c y. But notice what I have on the inside. On the inside, this is just the Fourier transform of f. So on the inside, this is just going to be f hat of c dy. As far as y is concerned, this is a constant. So I can factor this out of the integral, or just, treat it like a constant. And then what I'm left with, the integral is now going to be the Fourier transform of g. And so what we're left with is the Fourier transform of f times the Fourier transform of g. Okay, so what this tells me is that the convolution of these two functions, the Fourier transform of the convolution is equal to the Fourier transforms of the products of the functions. Okay, this is going to be a very useful fact that we come to. This is going to be a very, very useful fact that we use throughout the rest of this class pretty much. I'm not going to do question 8. You can do that on your own.